All right, now we're going to talk about acceleration. This ramp is not laying flat on the ground. It's got a little bit of a tilt to it. Now, watch what happens if it is flat on the ground. Exciting. Okay, now, the ramp's on a little bit of a slope. I'll let go of the ball. There's too much friction here. So we can't even overcome the friction of the ball. So I'm going to increase the slope just a little bit. Now the ball is accelerating down the ramp. So I want you to imagine making a particle diagram of this ball rolling down the ramp. Okay? What would it look like? Now, what would this look like? See what I'm saying? Right? Now, what would this look like? Okay, just a little bit later in the course, we're going to actually be quantifying this. We're going to quantify this today, but a little bit later, we're going to actually be working the angle and calculating precise accelerations. But this is a motion diagram, and now we're not doing constant velocity, we're doing acceleration. All right, so I drew these lines to represent the ramp, right? So this ramp has no slope. If we did a particle diagram, and particle just means we put a dot instead of drawing a picture of the car or ball or whatever we're doing. This is what a particle diagram would look like. And if we have one like this, it might look like this, because now this extra distance between each dot is showing us what? What's that word? Yeah, acceleration. This ramp's a little bit steeper, so each dot would be a little bit further along, and this one obviously may just look like that, right? So if you wanted to look at this a different way, and you were representing this all as just completely horizontal lines, if you looked at a graph like this, you would say, hey, whatever line this thing is on in real life is actually pretty steep. Does that make sense? So that's basically it. That's basically the sum of this. So I've got a little worksheet that goes with this. Now, if we're thinking about this worksheet, let's pretend, obviously we can see this would probably be on the slope. If we were graphing the velocity of this ball, first of all, would it be positive or negative, the velocity of the ball? Yeah, it'd be positive. And let me ask you one more question. Since this thing is accelerating, and we were labeling this, say, with an arrow, this one should be further down, right? Say with an arrow, what does that tell you about the velocity? It's changing, and not only is it changing, it's increasing. So if we were looking at a velocity over time graph like this, what would it look like?
Almost like the curve.
Well, yeah. Well, since it's increasing at a constant rate, then it would look like this. At the top of the line, at the top of the ramp, it's going 0, right? It's not moving. And then it gradually gets faster and faster. So that's what you'd be looking at. Does that make sense? And another thing, what if we had like a distance over time graph? Now, if velocity is increasing at a steady rate, then what's happening to the distance that's covered every second?
It's becoming more and more.
That's right. This distance and this distance and this distance are increasing, right? And it's increasing at a steady rate. Now, when we talk about derivatives or calculus or wherever you see this, right? What that steady increase in distance creates is not a straight line on this graph, but a smooth curve. And the quality of this curve doesn't change. Does that make sense? So a curve on a distance over time graph, a smooth curve, that shows a constant acceleration. A straight line on a velocity over time graph shows a constant acceleration. Right? And an orderly increase in distance of the dots of a motion graph show a constant acceleration. Does that make sense? Now, there's all kinds of stuff we can do with this. This means everything going in the positive direction like this means that the ball is rolling away from the start or away from you. If you're standing here and the ball is rolling back towards you, then that's a negative velocity for the ball, because velocity is relative to the observer. Does that make sense? So all of these graphs would be somehow backwards if the ramp was tilted. Our ramp was tilted like this, if the ramp is tilted like this. Does that make sense? All right, I'm going to give you, I'm going to give the people at home this worksheet to try. So this is the worksheet that you're going to be trying. And I'm also going to post your tables today. So your tables are going to be posted. So you can look on page 2. On page 2 of your tables, there are going to be a bunch of math formulas. So I'm going to help you out here with E, F, and G. For E, for E, F, and G, general mathematical expression for the relationship between X and T. Okay. The simplified acceleration formula is XF equals 1/2 AT squared. All right. F, general mathematical expression between V and T. Okay. Here is the simple acceleration formula. Acceleration is equal to change in velocity over change in time, or the amount of time went by. So we could put that for F and G. And if you feel like moving them around, you can. General mathematical expression between V and T. So you could put change in velocity is equal to acceleration times time. Does that make sense? Oh, I meant, yeah. And then for G, it says relationship between A and T. Well, that one's already answered. Acceleration is equal to change in velocity over time. These are all the same formula. This symbol, delta, means change. And another way to write delta V, another way to write that is just to write VF minus VI. In other words, your final velocity minus your initial velocity will give you the change in velocity. So if you're going 10 meters per second, then you sped up to 30 meters per second, the change in velocity would be 20 meters per second. All right? So have at this worksheet, you should be able to do it. Okay, so if we look at page 1, okay, if we look at page 1, there's your X. The distance is going to be steadily increasing and steadily increasing. All right, or greater and greater in a smooth curve. Velocity, boom. Acceleration is going to be positive and constant. Here are the formulas you can choose. All right, and the last one I didn't do for A right here, or for 1, I think we know that this would happen. We get further away. If we wanted to put an arrow on there, could be getting longer and longer. Does that make sense? Now, a couple things about this worksheet. Your E, F, and G can be the same, but this ball is coming back towards you. So this is going to be opposite of your graph. On this next page, this ball is rolling uphill, and you might be like, hey, this thing can't roll uphill. It can because it's got to run and go. If you look real closely, it says velocity is not equal to 0. So you have to pretend this ball was going fast, and then it got to the hill. Well, what would happen to it as it went up the hill? Good luck, people. You can do this. If you don't have a printer at home, you can just draw all these out. It's not like you have to copy any questions.